All right, well, I'm going to start. The heck is going on? All right. I'm gonna start. I wanted to mention this week, there are a couple of homeworks due, specifically these first two in the probability section. Those are gonna be due, this week, Friday at 5. We started the probability last time, the probability chapter last time, and we'll just keep going in that today. All right, but 2 homeworks due this week. Those first 2 right here. All right. So last time we looked at the introduction to probability. Today, we're going to start talking about how to calculate probabilities. Okay? So if we're trying to calculate probabilities, then we need to know what scenario we're in. In other words, what type of probability calculation that I should use. There's actually 3 different types of probabilities that we can utilize. One is called classical probability. So when you're calculating probabilities with classical probability, what you do is you assume that every outcome is equally likely. Remember we talked about outcomes of a probability experiment last time. So if we're dealing with classical probability, we essentially just say all outcomes are equally likely. We assume that, and then we can create a fraction to calculate the probability of something happening. We'll see an example of that later. With the empirical probability, we're going to utilize collected data to determine probability. So we do an experiment, we collect data on that experiment, and we use those data to figure out the probability of something happening. And then lastly is subjective probability. Subjective probability is where you use personal judgment or personal experience. So you're not doing formal calculations there. You're mostly doing like an opinion or an educated guess. So classical equal outcomes, empirical equally likely outcomes. Empirical uses collected data. Subjective is more of an opinion and educated guess kind of probability. Let's do an example of these. So for my classical probability, we're going to roll a standard die. Now, whenever we're rolling a die, some people, by the way, when they spell die, spell it D-I. Some people spell it D-I-E. Fine, whichever way you want to do that. I don't necessarily care. Now, whenever we're going to roll a die in this class, it's going to be the standard 6-sided cube die. All right. Better understand what I'm saying? The standard 6-sided die that you use in most games. Okay. And so the options are going to be 1, 2, 3, 4, 5, and 6. Now, with classical probability, we're going to ask, what is the probability of rolling the number 4? If you remember from shorthand, when I shorthand this, I'm just going to write a capital P and then either rolling a 4 or just the number 4 there as shorthand. So this notation means capital P is probability in parentheses of, and then whatever the event. What would you say the chance of rolling a 4 is?
1 in 6.
1 in 6, exactly. 1 in 6. That is classical probability. Classical probability says all the numbers are equally likely. So there's 6 options. The chance of getting a 4 is 1 out of those 6 options. And then you can also say, well, what's the probability of rolling an even number? Well, the chance that you roll an even number, of these 6 possibilities, 3 of them are even. And therefore, the probability of rolling an even number is 3 out of 6. Does that make sense? We okay with that? Now, just for the sake of knowing this, on Moodle, a lot of times the probabilities that we have are fractions, but in Moodle, a lot of times it's going to ask us for a decimal place. And the standard deal with probabilities is you round out to 4 decimal places. So a lot of times on Moodle, it's going to say round to 4 decimal places. And 1 out of 6, you just type that in on your calculator and you get 0.1667. Rounded to 4 decimal places. 3 out of 6 is 0.5. And so if it does ask you to round your probabilities out to 4 decimal places, go ahead and do that. By the way, this is just 0.5. This is rounded to 4 decimal places because there's only zeros afterwards, right? So there you go. So that's the concept of classical probability. Classical probability, when you're finding the probability using classical probability, you put all of the outcomes that the number of outcomes that you're looking of the event you're looking for divided by the total number of outcomes. All right. Oh, here's one. So everybody understands the classical probability? Number of outcomes in the event divided by number of total outcomes in the sample space. There you go. Empirical probability is this. Let's say we want to test a vaccine for some negative side effect. Now, how many outcomes are there? There's either you have this negative side effect or you don't. Right? That's the two outcomes. But they're not equally likely. So how would I find out what the probability of having a side effect is? Well, I do an experiment. And if we do an experiment, and we find that 24 out of 10,000 have the side effect, then that's going to determine the probability of an individual taking this vaccine and having a side effect. So the probability of having a side effect, again, it's not 1/2, just because there's two options, right? In this case, it's 24 out of 10,000 based on the collected data. All right. And again, if you wanted to round that, you could do 24 divided by 10,000 as a decimal, that's 0.0024. Again, just watch what Moodle asks you to do. If it asks you to round to 4 decimal places, do that. If it asks you to give the fraction, you can just give the fraction. Is that all right? So that's the idea of empirical data. Subjective is something like this. What if I am picking who is going to win the Super Bowl next year? You know, what's the probability that Kansas City repeats as Super Bowl champions next year? Or what's the probability that Detroit wins the Super Bowl next year? Notice you wouldn't say every team is equally likely. The teams that were really, really bad this year are probably less likely to win the Super Bowl than the teams that were really good this year, right? But you also can't utilize collected data because we don't have data collected on next year's Super Bowl champs. So you can't run that experiment over and over and over and over again. And so if you're looking at a question like, what's the probability that a specific team wins the Super Bowl next year? You're gonna have to make an educated guess. And that's subjective probability. Does that make sense? So we don't use subjective probability very much in our calculations in this class. We use a lot more of classical probabilities and empirical probabilities, just because subjective is more opinionated. All right? Does that make sense? So that's the idea, the different types of probabilities. So that's our basic calculations. Now we're going to get into some other ways to calculate probabilities. We're going to have addition rules, and then we're going to have a couple of different multiplication rules as well. So we're going to start with the addition rules. All right? So when I'm talking about addition rules, my assumptions are that we're doing a single experiment. But that experiment could have multiple outcomes, kind of like rolling a die, right? If I roll a die, could land on an even number, could land on an odd number, could land on all sorts of things. But we're doing a single experiment. That's the big one. And we're looking at multiple outcomes at the same time. Let's do an experiment. We're going to pick one card out of a standard deck. Now, a standard deck of cards has 4 different suits: spades, clubs, hearts, and diamonds. And in each of those suits, the numbers that appear on the cards are 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then there's also a jack, a queen, a king, and an ace. So there are 13 different types of cards in each of the 4 suits. So that means there are 4 sevens, there are 4 eights, 4 jacks, 4 queens. Everybody follow that? Most people have probably dealt with standard decks of cards before, but at least you want to go over that. So if there are 13 cards in 4 different suits, 13 times 4 gives you 52 total cards. So if we're picking one card and I say, well, what's the probability of getting a spade? A spade how many spades are there?
Did you say there's 14 of each?
13 of each.
13.
Yeah, so there are 13 spades. And you're picking out of 52 cards. Notice what I just did there was classical probability. Number of spades divided by the total number of options of 52. How about the probability of getting a face card? By the way, we call the jack, the queen, and the king face cards. Since there are 4 jacks, 4 queens, and 4 kings, there are going to be 12 face cards. So the probability of picking a face card using classical probability is 12 out of 52. All right. So that's classical probability. Now, let's think about how our addition rule is going to work. What's the probability of getting a spade or a face card? So a spade or a face card. So if you had to pick a single card from a standard deck, since you're picking out of the 52 cards, the 52 goes in the denominator. In the numerator, it's the total number of cards which are spade or face cards. So for instance, the 2 of spades is in that group. But also the jack of hearts is also in that group. Can I follow that? So if I had a pile of cards that were spades and face cards, how many cards would be in that pile? In other words, if I handed you a deck of cards and I said, take out all the spades and all the face cards, put them in a pile, how many cards would you get? Not 25.
It's not 13 plus 12.
You may think, well, it should be 13 plus 12, but here's the trick. There's a jack of spades that's in here and also counted here.
23.
22, I believe, right? Is that what you said? I can't hear very well. Maybe said 22 or 23. Should be 22. So if you think of the spades, there are 13. If you think of the face cards, there are 12. And we initially want to add those, but we have to throw out all the ones that are double counted. So the jack of spades, the queen of spades, can't draw a spade very well. There you go. And the king of spades, right? Those 3 cards have already been counted in here. So I need to take them out of this pile, essentially. Does that work? This group, the 3 that are both face cards and spades, those are the intersection, all right, of face card, known as intersection. I'll get to that in just a moment. Everybody get the concept though? So you have 13 spades, and then I have to add in all of the other face cards, the ones that are not spades. And the other face cards are the face cards minus the 3 spades I already counted. In one sense. Okay. I'm going to try to draw this as well using something called Venn diagrams. So Venn diagrams are just very basic pictures of circles. All right, think of that rectangle being symbolism for the entire deck of cards. We're going to have a circle that we're going to call face cards. We're going to have a different circle, which we'll call spades. And so what this is saying, essentially, is the probability of spade or a face card. Spade or a face card means any spade or any face card. So it includes the entirety of both circles, right? And so what you have to do is you have to add up the blue circle together with the part of the red circle that's left out. And the way we do that is you do blue plus, I take the face cards, and then I subtract sort of where they overlap here. That makes sense? Everybody kind of visually see why we're doing it the way we're doing it? So we take all of these options plus the red options, but we already counted this section when we counted the blue. So we throw it out of the red. Yeah.
Will we ever have like questions like this on Moodle that leave up? Cause like, I don't have numbers, so I wouldn't guess this normally, so.
Yeah. Yeah, so if on Moodle I ask you a question on cards, feel free to reference back to this slide here, or you can, look it up online or something like that. And also, hopefully, if you've printed out the notes, this is in your notes too. You can write it in your notes if you're going to, but yeah, you don't have to be an expert card counter or anything like that to get the right answers. You can look the basics of what a deck is. All right. So this is where the general addition rule comes from. Okay. If A and B are two different events, like getting spades and getting face cards, then the probability of A union B, that means the union of A and B. So it's like all of A and all of B thrown into a big set is equal to the probability of A plus the probability of B minus the probability of an A intersect B. That's the general rule for addition. And this comes from the counting, the set counting, what we call cardinality of sets. I'm gonna write that here and then point to some things. So the general addition rule. Rule. Addition of probabilities. That if we're doing the probability of A union B, that's equal to the probability of A plus the probability of B minus the probability of the intersection of A and B. Again, this is the union of A and B, which is a giant set or a big set which contains all elements from both. All right, oftentimes you'll see the word or. So what's the probability of getting either a spade or a base card? You guys remember that? That's what we just did. So you'll see the word or, so you can get either or. This is the union of A and B. Not, that's a union, excuse me, intersection. Union, intersection. The intersection of A and B, and it's a small set containing the overlap. So it's the elements that are in both A and B at the same time. And a lot of times you'll see the word and. So let me give you an example. If we're talking about human beings and traits of human beings, let's say blonde hair is one trait and brown eyes is another trait. Okay? Because I have brown eyes, I would be in the union of blonde hair and brown eyes. You understand that? Because I have brown eyes. I would not be in the intersection of blonde hair and brown eyes because I have brown eyes, but I don't have blonde hair. Does that make sense? So in my Venn diagram, if we're talking about blonde hair and brown eyes, I would be in the brown eyes, but not in the blonde hair circle. Does that make sense? I'd be basically living in this part, this section. So I'd be in a union because the union contains all the things that I've shaded here in green. So everything on the inside circles. But I would not be in the intersection. The intersection is just this sliver here. Everybody follow that? So that's the general rule for addition of probabilities. And we get that through some basic examples. All right. Now, here's the thing about having a general rule. We have a general rule, we can use it. Let's say we're in some other experiment. I don't even care what it is. Doesn't have to be picking of cards, doesn't have to be rolling of dice. It can be anything. Doesn't have to be picking people with blonde hair and blue eyes or blonde hair and brown eyes or anything like that. It can be any experiment. So in an experiment, we already know that the probability of A is 0.32. The probability of B is 0.25. And the probability of the intersection is 0.15. Find the probability of the union. The thing about general rules is that they work for any experiment, right? Therefore, if I have this general rule, this is an equation that holds in any experiment. So what I can do, if ever I have 3 of these numbers, I can plug in those 3 numbers and find the 4th number, the 4th probability. Everybody understand that? This general rule has 4 probabilities in it. If ever I know any 3 of those, I can plug those in and find the missing one using that general rule. And that's essentially what we're going to do here. We're going to say, well, we know the probability of the union has to be the probability of A plus the probability of B minus the probability of the intersection. The probability of the union is the one I don't know, so I'm just going to keep that as probability of the union. Probability of A, it tells me is 0.32. Probability of B, it tells me is 0.25. And the probability of the intersection, it tells me is 0.15. Now, this is really easy to solve because all we have to do is simplify and combine like terms on that right side. 0.32 plus 0.25 minus 0.15 is 0.42. And so now we know the probability of the union. Does that make sense? So if we have any probability experiment and we know 3 of these numbers, we can plug those in and find the 4th missing number, in other words. I want you to do that on this one. Now, for this one, you're not given you're given the union and not given the intersection. So try to find the probability of the intersection on this one. All right, so let me go through this one. So it said that the probability of the union was 0.9. The probability of A was 0.46, and the probability of B was 0.65. And it's asking us to find the probability of the intersection. Now, there's more than one way to go about solving this equation. I'm going to go through the way typically we would. Typically, what you would do is you combine like terms. So on the right-hand side, you'd add 0.46 with 0.65. That's 1.11. Then we subtract 1.11 from both sides. You get negative 0.21 is equal to negative probability of A intersect B. Then because you have a negative 1 or just a negative coefficient, you divide both sides by -1. And you get 0.21 as the probability of A intersect B. Is that right? So 0.21 is the probability of the intersection. That don't make sense, Solomon, that way? Hopefully that's something we've done before, solve equations with one unknown. I want you to try this one and see what happens. Probability of A, 0.29. Probability of union, or probability of B is 0.75. Probability of union is 0.60. Oh, shoot. All right. Now, mathematically, this is all gonna be just fine. All right? Mathematically, we're gonna put this in. We're gonna get 0.29 plus 0.75, that's 1.04. We're gonna subtract 1.04 from both sides. Get negative 0.44 equals negative probability of A intersect B, and then divide by the -1 on both sides. And you get 0.44 is equal to the probability of A intersect B. Okay, 0.44. Everybody calculate that. And for a moment you think, well, yeah, that was just like the previous one, right? It's just like the previous problem. I mean, nothing really was changed there. However, I do want to say, even though you can mathematically do this, there is a feature to this one which actually was problematic. Whereas this one wasn't. And the way you should look at this is through the Venn diagrams again. Now, I'm not gonna try to trick you or anything like that on a test. But I do want to say this one is a problematic example. I created it because it was problematic. And the reason why this is problematic is that if you think back to that Venn diagram, the union is everything in A together with B. That means the union needs to be the biggest number around out of these four probabilities. Everybody follow that? And the intersection, well, let me just draw two diagrams, one below the other. So if you think about the union is all of the stuff inside both circles. The intersection is just where both circles overlap, right? So the union needs to be the biggest probability and the intersection needs to be the smallest for it to be an actual legitimate working issue. In this case, the intersection actually came back bigger than A, and the union came back smaller than B. So that's a problem, technically. All right. I'm not going to give you a trick question that says, well, technically, does this work or anything like that. If I give you a question, I will give you one where the union gives you the biggest probability and the intersection gives you the smallest probability. But there are certain constraints around what can happen and what can't happen. And the big constraint is of these four probabilities, the probability union is the biggest, and the probability of the intersection is the smallest, and the probability of A and the probability of B, those are the middle ones. Does that make sense? Yeah. Again, I'm not here to trick you, but I do want to mention that before we move on to our other rules. That in the general rule, here, the probability union needs to be the biggest number out of those four, and the probability of the intersection needs to be the smallest number out of those four, just because of the way unions and intersections work, right? With sizes. All right, so that's the general addition rule. There are other addition rules as well. There's something called a complement rule, which we're not going over right now. If you get into probability and statistics class, we go over some other complement rules. We talk about the difference of mutually exclusive versus not mutually exclusive events. But this general rule works for them all. As far as addition goes, all right? So now we're gonna start looking at some multiplication rules. Now there's gonna be actually two different rules we will use. One for dependent events and the other for independent events. Now let me start out by multiplication in general. These multiplication rules arise when we do multiple experiments in a row. So instead of me rolling one die, maybe I roll two dice in a row. And I say, what's the probability of getting 4 on the first one, and what's the probability of getting another 4 on the second? Stuff like that. Or maybe I flip a coin, and then I flip another coin, and then I flip another coin. So I flip 3 coins in a row, and I say, what's the probability that the first one lands on heads, the second one lands on tails, and the third one lands on tails? Or maybe I pick now let's pick 3 people in a row, and I say, what's the probability that the first one is left-handed? What's the probability that the second person I pick is left-handed? What's the probability that the third person I pick is left-handed? Get that? So with these multiplication rules, you're doing essentially 2 different experiments, or 3 experiments, or 4 experiments all in a row. And you're looking at the outcome of one event, the first one, versus the outcome of the second event. Now, dependent events are when the outcome of the first affects the outcome of the second. Independent events are where the outcome of the first does not affect the outcome of the second. Let's try to figure out whether features are independent or dependent. Let's say I pick a person at random in the United States. And I say, we're going to look at that person's gender, and we're going to look at whether or not anyone in their well, let me restate that. Whether or not they themselves have testicular cancer. Okay. Are the concepts of gender and testicular cancer dependent or independent? Well, it should be fairly obviously that they're dependent. If your gender is female, your probability of having testicular cancer is infinitesimally low, right? If you're male, your chance of testicular cancer is much higher than if you're female, right? That makes sense? So those are dependent. The probability of one affects the other. If I know somebody has testicular cancer, then I have a good shot at guessing their gender. A very good shot. How about this? If I have 50 people randomly selected in a room and flipping a coin, if I know the person who's flipping the coin's gender, am I more likely to guess whether that coin heads or tails? You should say no, right? The person who's female who flips a coin and the person who is male who flips the coin have an equal shot of getting heads on that coin flip. So those would be independent. Your gender would have nothing to do with whether or not when you flip a coin, it's more or less likely to land on heads. How about this third one? I want you to think of this. What if we roll a roulette wheel and it lands on some number, a little ball lands in some number. The second roll of a roulette wheel, is that going to be affected by the first roll of the roulette wheel?
Stupid, but when I think of roulette, I think of a gun.
Oh, yeah, that's a different thing. That's Russian roulette. Yeah. No, roulette is a casino game. Yeah, Russian roulette would be a whole different, that's a whole different ball game there. No, roulette is just a casino game where a little ball rolls into one of 38 different slots on a little wheel, all with different numbers. And then the second roll, you pick up the ball, you roll the wheel again, you drop the ball again. All the probabilities are now the same when the second ball drops, when you drop the ball the second time. So the first and second roll of roulette wheel are independent. They are not, the outcomes are not affected by each other. That work? How about this? If two people have a child and that child has some sort of a rare disease or a rare condition, is their second child more likely to have that rare disease than a child from the general public? The answer is yes. The first child having some rare disease is an indicator that whatever genetic components make up that rare disease, the parents have them, right? So a couple's second child is more likely to have that rare disease if the first child has that rare disease too. Does that make sense? So that would be dependent. One depends on the other. One's affected by the other. Now, the easier of the two rules is the independent multiplication rule. So we're going to start out with that. If events don't affect each other, then the probability of both of them happening is the probability of them individually happening multiplied times each other. In other words, the probability of A and B both happening is just the probability of A times the probability of B. That's the independent multiplication rule. Probability of A and B both happening is the probability of A times the probability of B. Now let's think about why this rule works. This rule works. I always like to think of coin flips here. Let's say I want to flip a coin twice in a row. Now, the nice thing about flipping a coin is that as long as it's a fair coin, it's got a 50-50 shot of being heads or tails. Well, my first flip could be heads. And then my second flip is equally likely to be heads or tails again. Okay. So if we say, what's the probability of getting heads on the first flip and heads on the second? That's the probability of getting heads on the first flip multiplied times the probability of getting heads on the second flip. Like I said, probability of heads, there's only two options. So probability of heads in the first flip is 1/2. On the second flip, since we have independent flips, it's also 1/2. When you multiply fractions, you multiply their numerators and then multiply their denominators. And sure enough, heads is one of the 4 options present in this diagram. You don't have to draw the diagram or anything. I'm just trying to give you some motivation on why that works. So the multiplication happens because there's lots of different outcomes branching out. Okay. And once you do that once, you think of, well, if you have lots and lots of outcomes, then it just kind of explodes, right? So the number of outcomes explodes. It's really, really big. So independent multiplication works because the number of outcomes grows by multiplication. 2 times 2 is 4, 3 times 3 is 3. 3 times 3 is 9, et cetera, et cetera. Okay. So let's go to our roulette wheel example. All right. So in the casino, there's this thing, it's a roulette wheel. And again, you don't need to be a great expert on the casino. If I ever ask you to do some calculations with a roulette wheel, I'll give you the basics of what you need. The basics of what we need to know for this class is that on a standard roulette wheel, there are 38 slots. 18 of those slots are colored in red. 18 of those slots are colored in black, and 2 of those slots are covered in green. Now, this is the American version roulette wheel. In Europe, they do a 37 slot, but they do it in America too, but it's called European roulette wheel, it's 37. We're gonna always deal with the 38 slot roulette wheel, right? So 18 red, 18 black, 2 green, and they're all different numbers. Okay. The numbers 1 through 36 cover the red and black numbers, and then the green slots are labeled 0 and 00. So it says, what's the probability that you get green and another green? So 2 greens in a row. And then it says, what's the probability that you get 2 reds in a row? So first off, again, this was one of our examples in the independent versus dependent. We saw that this should have been independent, so we can use independent multiplication rule. So what I can do to find what's the probability of getting green on the first roll and green on the second roll is I can just multiply the probability of getting green on roll 1 times the probability of getting green on roll 2. If there are 38 slots, 2 of which are green, then the probability of getting green using classical probability is 2 over 38. If I want to get green twice in a row, I do 2 over 38 times another 2 over 38. Now I want to give you some options of how to utilize your calculator for a second. I'll do that in just a minute. What I'm going to do right now is just say, when I multiply fractions, 2 times 2 gives me 4. 38 times 38 gives me 1,444. I'll come back to that in just a moment. Okay. All right. How about the probability of getting red and then another red? Once I've done this once, I'm not going to write this middle step. I'm just going to go straight to the fractions. What's the probability of rolling a red on a standard roulette wheel? Yeah, since there's 18 reds out of 38 options, it's 18 over 38. And since those are independent, I can multiply them. Again, multiplying the numerators, I get 324. Multiplying the denominators, I get 1,444. Actually, I'm gonna deal with this one just on your calculator, just real quick. So let me, swap the video. Which camera? There you go. That's the one I want. Good. All right. So the way I did that, I just did 18 times 18 and then 38 times 38 separately to give me that 324 over 1444. Okay. However, if you wanted to, you can do this in fractions and just say 18 out of 38 multiplied times another 18 out of 38. Now that'll bring you right to a decimal. And if Moodle asks you for a decimal rounded to 4 decimal places, you'd write 0.2244. Now here's the thing. In both the TI-84 and the TI-30, if you ask this to now convert to a fraction, you're gonna get a fraction that looks slightly different than the one I just got. The reason it looks slightly different than 324 over 1444 is that this is the reduced fraction. Okay? Your calculator is always going to give you the reduced fraction version of the answer, regardless of whether you have a TI-84 or a TI-30. Okay? And the only reason I say that is if you're looking up on some answer key somewhere and you got 324 out of 1444, and on some answer key, you see it as 81 over 361, or on some answer key, you see it as 0.2244, don't be thrown off. All three of these numbers are essentially the same. Okay, one is reduced, one is just multiply, and the other is the decimal version. Okay. All right. I just want to warn you about that. Every time I write a fraction on the board, just realize there's other ways that the fraction can be written. Okay. I tend to just multiply the numerators, multiply the denominators, and move on. All right. I want you to try this page on your own. Find the probability that a person rolls a green, then a red, then a black. So a green number on the first roll, then a red number on the second roll, then a black number on the third roll. And then what's the probability that a person rolls 3 reds in a row? All right, so let me go through this. Shouldn't take long once you figure it out, the basics of the process. Getting a green on the first roll is 2 out of 38. Getting a red on the second roll is 18 out of 38. Getting a black on the third roll is also 18 out of 38. Now, I multiplied all the numerators together. 2 times 18 times 18 give me 648. And then I multiplied the denominators. 38 times 38 times 38 gave me 54,872. Okay. But again, if you typed in your calculator and got a different answer, it won't be different numerically, but it just look different. That's fine too. Similarly, red times red times red. Well, red times red times red is 18 over 38 times itself 3 times. I once again multiplied all the numerators. I got 5, 8, 3, 2 on top. And in my denominators, once again, I got 54,872. All right, does that make sense? All right. Again, there are other, that's not the reduced fraction. You could write the reduced fraction if you want. Your calculator converts things into reduced fractions if you wanted to. Same thing, it can convert that into decimal as well if you wanted to. Both of those. All right. No questions? All right, well then we're gonna stop here. Next class, we'll come back in. We'll finish this independent multiplication stuff up, and then we'll get into how dependent events work and how probability is calculated for dependent events. That work? All right, I'll see you next time.